All right, so I'm going to begin by quickly going over a little bit of what I talked about last time. So last time I talked about span and linear independence. And I wanted to review just a little bit of what we covered regarding those two topics. So if we have a vector space V, and here I have some vectors V1 through Vk in our vector space. So let's just recall these vectors are set to span our space V if this equation has a solution for every vector B in V. Equivalently, you can say that they span the space V if every vector in V can be written as a linear combination of these vectors V1 through Vk. Now, for linear independence, we see that these vectors are independent if this equation here has a unique solution. So this equation always has at least one solution. Namely, it always has what we call the trivial solution, where the coefficients are all equal to 0. So if that's the only solution, if the solution is unique, then they are independent. Okay. So let's talk about how span and linear independence are kind of related. All right, so give me a minute. Oh, okay. Okay, so when we are working problems, so to check if vectors span a space, we want to set up this equation, and we want to see if this equation will always have a solution. Independence, we've set up a very similar equation. The only difference between these two equations is the right-hand side. Now, when we're doing our problems, these equations, we usually end up writing them as a system of equations. And again, the left-hand side of these equations is the same. It's going to have the same coefficient matrix when you set up the system of equations. Now, span meant that the equation always has a solution for any b. And so for there to always be a solution, that will happen if and only if every row of the matrix A has a pivot in it. And when we're looking at this equation, AX equals 0, for independence, we need this equation to have a unique solution. And a unique solution will happen if and only if a column of A has a pivot instead. Okay. And so these are the things I talked about in my last video. And so today I'm going to talk about the definition of a basis for a vector space. All right. So again, we have some vectors v1 through vk. We see that these vectors form a basis for the space V if they span V, and 2, if they are also linearly independent. Okay. All right. Now, let's also talk about dimension as well. And then after that, I'll do some examples. So first, I'm just going to state a fact. So it's a fact that any vector space can have more than one basis, okay? But every basis for a given vector space will have the same number of vectors in it. Okay. All right, so then the dimension of a vector space is defined to be the number of vectors in any basis for the space V. All right. All right, so now I'm going to do a whole bunch of examples right now. So I'll start with some pretty simple examples. So I want to talk about the standard basis in Rn. I'll use R3 as a particular example. All right, so any vector in R3 can be represented in this form, x, y, z. Oops. All right. And here, I'm going to rewrite it as x and then times 1, 0, 0, plus y times 0, 1, 0, and plus z times 0, 0, 1. Okay. So these vectors that you see here, the vector is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this is what we call the standard basis of R3. So it is a basis in particular. So here we see that every vector in R3 can be written as a linear combination of them. So that shows that they already span all of R3. And then if we set this combination equal to 0, it's easy to see the only way for this to be 0 is for x, y, and z to be 0. So you'd also have a unique solution there, so they'd also be independent, all right? And so you can generalize this to the standard basis in Rn for any n. So it consists of the vectors that have 1 and 1 component and 0 everywhere else. Okay. Oh, whoops. All right. So that's one example of a basis in Rn. Now, regarding dimension, so dimension was defined to be the number of vectors in any base for the given space. So here in R3, the standard basis has 3 vectors in it. So therefore, we could say that the dimension of R3 is equal to 3. And any basis for R3 would have to have 3 vectors in it. Likewise, for Rn in general, the standard basis will consist of n vectors. And because you have a basis with n vectors in it, you can say that the dimension of Rn would be equal to n. And every basis for Rn is going to have n vectors in it. All right. Quickly, I'm also going to talk about standard basis for the space of m by n matrices. I'll look at the space of 2 by 2 matrices as a specific example. Okay. So every 2 by 2 matrix can be written as a combination of 4 matrices. So these matrices, just like the standard basis for Rn, these matrices have 1 and 1 entry, and then 0 for the remaining entries. All right, so then we see that these 4 matrices already span the space of 2 by 2 matrices, because every 2 by 2 matrix is already a linear combination of them. And then we can see that the only way for this combination to equal the 0 matrix would be for A, B, C, D to all 0. So they'd also be linearly independent. So this would be a base for M 2 by 2. And this is what we call the standard basis for the space of 2 by 2 matrices. And because this basis has 4 elements or 4 vectors in it, we can say that the dimension of M 2 by 2 would be equal to 4. And any other basis for this space is going to have 4 matrices in it as well then, okay? All right, so you can generalize for the space of M by N matrices. Its dimension is going to be M times N. And there's also a standard basis for this space. And again, it would just be the M by N matrices that have a 1 and 1 entry, and then 0 in all the other entries, okay? Yes, so we'll get to that. All right, finally, you guys also have some examples of polynomial spaces, so let's talk about that real quickly. Okay, so again, I'll do a specific example, so let's look at the space P2 first. So remember, P2 is the space of all polynomials of degree less than or equal to 2. So any polynomial in P2 can be represented in this form, a plus bx plus cx squared. And again, I'm going to rewrite this in a particular way. So notice I can write this as a times the constant polynomial 1 and plus b times the constant polynomial x, and then, well, just the polynomial x rather, and then plus c times the polynomial x squared. Okay. So thinking of 1x and x squared as polynomials, these guys, we see that they span P2 because every polynomial in P2 can be written as a linear combination of them. And then likewise, the only way to form a combination of them that will produce the zero polynomial would be if a, b, and c were all equal to 0. And so because the only way to form the zero polynomial is to make all the coefficients equal to 0, that makes them independent. So therefore, they do form a basis for P2. So this would be the standard basis of P2. Okay. And because there's 3 polynomials in this basis, that means the dimension of P2 is going to be 3. And every other basis of P2 is going to have 3 polynomials in it. And then finally, I'm just going to generalize to Pn. So the polynomial is 1, x squared, and so forth, up to x to the n. This will give us the standard basis for Pn. And the dimension of Pn is going to equal n plus 1, because there are n plus 1 polynomials in this list. All right, so I guess I will address some of the questions that are being asked now with some more examples. I was going to do some other examples first, but I think I'll go ahead and do these first instead. Yeah, so let's consider some different vector spaces now. In particular, I'm going to consider subspaces, some of the spaces we just talked about. So I want to start with, as an example, the space of 2 by 2 upper triangular matrices. Okay. Now, if you look at what I've done in the first 3 examples, so in this example, I took a generic element of P2, and then I was able to use the variables in it to write it as a linear combination. And from there, I was able to find a basis for P2. I did something similar for M2 by 2, where again, I took a generic element of my space, and then I used my variables to write it as a combination of certain matrices, and that ended up giving me a basis. So this general strategy, you can apply it to any other space that you encounter. So here I have the space of 2 by 2 upper triangular matrices. So if we just write out what a generic element of this space would look like. So here I have a generic 2 by 2 upper triangular matrix. Now I'm going to use the variables here. I'm going to write it as a combination of some specific matrices. In this case, you see that I can write it as a combination of these three matrices in particular. So then these three matrices will give us a basis for the space of 2 by 2 upper triangular matrices. So they automatically span the space already, because here we already show that every 2 by 2 upper triangular matrix is a combination of them. And then the only way for this combination to equal 0 would be for the coefficients to be 0. So again, they'd be independent, again, sort of almost automatically. Okay. So here we see that the dimension of U 2 by 2 would be 3 right now. If we try to think in general, what would the dimension of the space of all n by n upper triangular matrices be? Do you guys have any idea what that might be? No, for, okay. So let's think about it, right? Let's look at our example and let's see if we can generalize. Okay, so a generic upper triangular matrix, it will have entries along the diagonal, and then it'll have entries in the upper half, but not the lower half, right? Now, notice that we get one basis element for each of the variables that we used to write out like a general vector in our space. So like here, because we used 3 letters, that's why you ended up with 3 basis vectors. So we sort of want to count how many letters would we need to use to represent an upper triangular matrix. Okay. So we need to use n letters because there are n diagonal entries, right? Now, in addition to filling out the n diagonal entries, I also want to fill out all the entries that are above the diagonal. So let's think what that would be. So there will be n squared minus n entries that are not on the diagonal. Right? So half of these would belong in the upper half above the diagonal. The other half would be below the diagonal, but those would all be zeros, so I wouldn't have to count them. So then this would give you like a general formula for the space of n by n upper triangular matrices. Does that make sense to you guys? Do you understand that logic in obtaining that formula? All right, so let's do a couple more examples like this. Yeah, so I was trying to count the number of entries that would not B on the diagonal. So there's n squared entries altogether in an n by n matrix. There's n of them along the diagonal. So therefore, there'd be n squared minus n entries off of the diagonal. Okay. Okay. I won't do anti-symmetric matrices, but I will do symmetric matrices instead. Oh, that's too complicated. So I'll start with the space of 2 by 2 symmetric. Well, I'll do maybe 3 by 3 first. Okay. So let's look at 3 by 3 symmetric matrices. Let's say I want to find a basis for this space. Okay. So again, the strategy will be to first just write out what a generic element of the space will look like. So a generic 3 by 3 symmetric matrix is look something like this. Okay. Once you're able to write out what a generic element of the space looks like, use the letters or the variables and use them to form a combination of specific matrices. So here I can write it as A times the 1 here, then plus B times. But for B, I'd have a 1 in this entry, in this entry. And then I can do plus C times. So I'd have a 1 in the corner entries here. Plus D times. Okay, so for D, I'd have a 1 only in the middle entry. Plus E, and then for E, I have 1s in these two entries. And then for F, I would have just a 1 in this last entry. So just to save time, I'm not going to fill in all the zeros. Okay. All right, but then these 6 matrices that we ended up with, these 6 matrices are going to form a basis for the space of 3 by 3 symmetric matrices. And because there are 6 vectors, if you will, in this basis, we could say that the dimension of the 3 by 3 symmetric matrices would be equal to 6. Okay. Again, it's relatively clear when you do this that these matrices will in fact be a basis. They are span the space because already we showed that every 3 by 3 symmetric matrix is a linear combination of them, so they are a span. Then the only way this combination will equal 0, well, the only way for this to be 0 would be for all the coefficients to be 0. So that shows that they are going to be independent. If I generalize to n by n symmetric matrices, and I would think, what would its dimension be? So we can think about what the dimension would be by thinking about how many letters would we need to use to represent a generic n by n symmetric matrix. And if you think about it, it's the same as the number of letters we would need for an n by n upper triangular matrix. Because just like with the upper triangular matrices, we need letters for each of the diagonal entries. And then we need letters for everything above the diagonal. We don't need any additional letters for everything beneath the diagonal, because these are just going to be like reflected across the diagonal. So once you fill in the upper half, you already have the lower half automatically. You don't need any other letters for that, okay? So it actually gives you the same dimension as the space of n by n upper triangular matrices. All right, so any questions about that example? I'll do an example of polynomials next. Okay. Yes, that's correct. So those 6 matrices ended up giving us a basis for the space of 3 by 3 symmetric matrices. So since you got 6 matrices in that basis, therefore the dimension would be 6. You can also say that from that we can also conclude that every basis for a space of 3 by 3 symmetric matrices would necessarily have 6 matrices in it as well. Okay. Okay. Now let's look at an example with polynomials. So let's consider the subspace of, I'll do the subspace of P3, consisting of polynomials satisfying P of, well, I'll do P of 2 equals 0. Okay. So we're looking at this subspace of P3, and again, we want to find a basis and then figure out what its dimension be. So the strategy that we've been doing so far is to first, we want to write out what does a generic element of this look like. So this one's a little bit more difficult, but not much more difficult. Okay. So first, it's going to be a polynomial P3. So we know that it's going to be of degree at most 3. So we'll start with something like this. All right. But now, in addition, it also has to satisfy this equation. So let me see what this equation will say about this polynomial here. So if I try to actually plug in 2 for x, I'm going to get a plus 2b plus 4c plus 8d, and we're saying that this has to equal 0, right? So this tells me that the variables that I used here, they have to satisfy this equation. And what I'm going to do is I'm going to rearrange this equation. I'm going to solve for a right now. So I'll get this is a. So what I can do is I'm going to take this expression for a and I'm going to sub it back into the expression for p of x. So now we'll have p of x is minus 2b minus 4c minus 8d, and then plus bx plus cx squared and plus dx cubed. Okay, so then this is what a generic element of this space is going to look like. So now that I have this form, I'm going to do what we've always done, and I'm going to write it as a linear combination of certain polynomials using these variables b, c, d as the coefficients. So I can write it as b times x minus 2 plus c times x squared minus 4 and plus d times x cubed minus 8. Okay. So then if I focus on these three polynomials that we ended up with, so I haven't been emphasizing this in the examples, but I think it is just worth pointing out that so these polynomials, they are elements of our subspace. Okay, so they are of degree at most 3, so they are in P3. And if you put in 2 for x, you see that all three of them are going to become 0. Okay. So yeah, we've got 3 polynomials or 3 vectors in this space. We've already shown that any vector in this space is a linear combination of them. So that already shows that they span our space. And then the only way for everything here to be 0 would be for b, c, and d to be 0. So they're also going to be independent. So this will give us a basis for this subspace of P3. Okay. And because there are 3 vectors or 3 polynomials in this basis, that means the dimension of this subspace is going to equal 3. Yeah. All right. So any questions about that example? Okay. So if you're given a space and you're asked to find a basis for it, as well as its dimension, here using the general strategy. So try to write out a generic element of that space. Then use the variables in that expression to and like write it out as a linear combination using those variables as the coefficients. That pretty much will give you a basis for that space. And then once you have the basis, you can also figure out the dimension by looking at the number of vectors that were in that space. Now let me do just a couple more examples before I talk about some other stuff. I'm going to go back to the space of 2 by 2 symmetric matrices. So this time, I'm going to write out 3 2 by 2 symmetric matrices. And so given these 3 particular matrices, we want to ask, do these 3 matrices form a basis for the space of 2 by 2 symmetric matrices? Okay, so let's quickly go over the strategy for this type of problem, where you're given certain vectors in that space, and you want to know if they form a basis or not. So remember that to form a basis, they have to span and be linearly independent. So to check if they span, you want to set up this equation and see if it always has a solution, no matter what the right-hand side b is. For independence, you want to set up this equation instead and check if it has a unique solution. Now, when you set up these 2 equations, they're going to become a system of equations in your problems. And the only difference between the system of equations is just going to be the right-hand side being b or 0. The left-hand sides were the same. And so for span, you're checking if there's always going to be a solution. And again, for that to be the case, every row will have to have a pivot. For independence, you're checking that there will be a unique solution. And for that to be the case, every column is going to have a pivot. So let's try to keep that in mind, and I'm going to do 1 or 2 examples. So here I've got an example with matrices. Okay, so I'm going to first form a combination of these 3 matrices that were given. Okay, now if I'm checking span, then I would set it equal to a generic 2 by 2 symmetric matrix. For independence, we'd set it equal to 0 instead. And in our case, you would end up with a system of equations. So if I look at the left-hand side, I focus on just like the first entry. You're going to the equation 0c1 plus 2c2 plus 1c3. So that you would get on the left-hand side. Looking at the second entry next, you're going to get c1 plus 1c2 plus 1c3. If you look at the third entry, you actually get the same equation. Because it was symmetric, these had to be the same. And because it's the same, you don't really need to write it again. So I'll go ahead and just ignore it because it's the same as the second equation already. And then finally, looking at the last entry, I'm going to get 0c1 plus 1 C2 plus 1 C3. Okay. So this was what we'd have on the left-hand side. The right-hand side would depend on when you're checking span or when you're checking independence. But all we really need to focus on to check if they span and are independent, all we really need to do is look at the coefficient matrix. Okay, so here this would be the coefficient matrix for the system of equations. And then we're the rule that we talked about earlier for span and independence. So you'll know that they span if this matrix has a pivot in every row. You'll know that they're independent if this matrix has a pivot in every column instead. Okay. So if we just do some elimination real quickly, I'm going to swap the first and the second row first. And then it's not a big deal, but I'll go ahead and swap the second and third rows. And then if I just do one more row operation, we'd end up with this upper triangular matrix. And now that we've reduced it to the row echelon form, we see that we have a pivot in every row as well as every column. So therefore, they would both span and be linearly independent, and therefore they would be a basis for our space, okay? So let's see here. If I call these matrices, I'll just call them UVW. Here we see that UVW both span this is two by two symmetric matrices and are independent. So therefore, it would be a basis for our space. Yeah. Okay, so questions about that? Yeah, end up with a duplicate equation like we had here because we were dealing with symmetric matrices. So like the equations that we got from like the second and third entries of the matrix same. So if you get redundant equations like that, you can just ignore them. In the event that you did include them, you still get the same conclusion though. In the end, so it's not a big deal if you include them or not. But you may as well ignore them so that's a little bit less to write. All right, now I will one more similar example. Just work with polynomials. Okay, so let's say I'm working with the space of polynomials with degree less than or equal to 2. let's suppose I have these three polynomials given. So first polynomial will be 1 minus x plus x squared. The next, let's say we have another polynomial, q of x, which is 1 minus x squared. And then let's say I've got one more polynomial. Okay. And then for these three given polynomials, again, we want to check, do they form a basis for the space of P2? So to check if they're a basis, we would first set up a linear combination of them. So I'm going to do C1 plus P of x plus C2 times Q of x plus C3 times R of x. And so if I were to check for independence, then I would set this combination equal to the 0 polynomial. And then I'd try to solve for C1, C2, C3. So this would be for independence. And then if I wanted to check if they span the space, then I would set this combination equal to, rather than setting it equal to 0, for span, you're supposed to set it equal to a generic element of your space instead. But the right-hand side is not going to matter too much. What's going to matter more is what you end up with on the left-hand side. What I'm going to do right now on the left-hand side is I'm going to just rearrange everything. I'm going to rearrange so that the constant terms are grouped together, that the terms with an x are grouped together, and then the terms with an x squared are grouped together, okay? So looking at the constant terms, we're going to have a C1 plus a C2, and that's it. For the terms with an x, we're going to have minus C1 x, and then plus 2 C3 x, okay? And then for all the terms with an x squared, we're going to have C1 x squared. We're going to have a minus C2 x squared. And then I'm going to get a plus 3 C3 x squared, okay? And again, I don't care too much about my right-hand side, but I'll just carry it over at least one more time. Okay, now here the idea for polynomials is that, let's say I were checking independence, then for this to equal the 0 polynomial, I would need the coefficients to be equal to 0. So I'd need C1 plus C2 to be 0. I would need this to equal 0 as well. And finally, I would need this to equal 0. So that will give me a system of equations. This would give me the left-hand side of that system of equations. Right-hand side would be zeros. For independence, it would just be like ABC if I were checking span. But again, all we really need to do is focus on the coefficient matrix that we get here. And then again, just remember the rule that you can follow is for the span, there has to be a pivot in every row. Remember that to be independent, there has to be a pivot in every column. Okay. So if we just quickly reduce this matrix, just to see where all the pivots are going to be. So do one more operation here. Okay, so now that we have it in a row echelon form, see that we do have a pivot in every row and every column. So therefore, we can conclude that the three polynomials that we were given do in fact give us a basis for the space P2. All right, so then any questions about that? If not, then I'm finally going to talk about some more concepts. So now I'm going to talk about the fundamental subspaces of a matrix. So you've already seen some of these fundamental subspaces already. So we've already encountered the column space of a matrix A, which is usually going to be notated as C of A for the column space of A. So it was defined to be the span of the columns of the matrix A. Last time I talked about how you can also view the column space of a matrix A as being equal to the set of all vectors B for which the equation AX equals B has a solution. I also talked last time about the null space of a matrix, which will typically be denoted by n of A for null space of A. So this was defined to be the set of all solutions to the equation AX equals 0. So in addition to the column space and the null space of a matrix, There's also another one of the fundamental subspaces, the row space of A. Which I think in this class you'll see denoted as R of A for the row space. But really the row space of A is defined to be the column space of A transpose. Because the columns of A transpose were the rows of A, so it kind of makes sense. In words, we can say the row space of A will be the span of the rows of A. Thinking of the rows of A as vectors. Okay. And then there's one more fundamental subspace, which we call the left null space of A. And the left null space of A is simply the null space of A transpose. Okay. Ultimately, there's 4 fundamental subspaces. So you have the column space of A, the null space of A. Then you also have the column space of A transpose and the null space of A transpose. And the column space of A transpose is the row space of A. The null space of A transpose is the left null space of A. Okay? And I'm going to sort of quickly talk about how to find a basis for each of these 4 fundamental subspaces. I'm just going to illustrate that with an example. So I'm going to create a matrix right now. All right, now, if you're given a problem where you want to find a basis for each of the 4 fundamental subspaces, it's easiest, in my opinion at least, to first reduce your matrix all the way into the reduced row echelon form. So for me, that would be the first step, is to reduce your matrix into the reduced row echelon form. Now, a question that I get a lot is, do we have to reduce that all the way to the reduced row echelon form, or can we simply leave it in the row echelon form? So the answer to that is technically yes. You can just go to reduced row, or sorry, you can just reduce to a row echelon form. You don't have to put it all the way into the reduced row echelon form. But I do find that problem is easier, in my opinion, if you go all the way to the reduced row echelon form. Okay? And so that's just what I'm going to do. Now, in the interest of time, I'm going to go ahead and just skip to the result. So I'm not going to do all the row operations. But if you did all the row operations, you would find that the reduced row echelon form looks like this. Okay? All right. Once we get it into the reduced row echelon form, we can immediately get a basis for the column space and the null space. So we'll do that, or column space and row space first. So we'll do that. So first, let's look at the column space. So here's how you get a basis for the column space of your matrix. So find the columns that have the pivots in them. Okay. In this case, we have pivots in columns 1, 2, and 4. Okay. So if you take the corresponding columns in the original matrix, these columns from the original matrix A will be a basis for the column space of A. So meaning in this example, since we had pivots in columns 1, 2, and 4, that means if I take columns 1, 2, and 4 from the original matrix, those three vectors will be a basis for the column space of A. Okay. So then I'm just going to write down the first, second, and fourth columns of A. And these three vectors will be a basis for the column space. Okay. So they will end up spanning the column space, and they will also be linearly independent. Now, in the meantime, let me also quickly talk about the dimension of the column space. So in this example, the dimension of the column space would be 3, because we found 3 vectors in a basis for the column space. Now, in general, the dimension of the column space is also known as the rank of the matrix. And because you get a basis vector from each pivot, you can think of the rank of A as also being equal to the number of pivots in the matrix. So rank is the number of pivots. It's also the dimension of the column space. Okay. Next, to get a basis for the row space, simply take the rows with pivots in the reduced matrix. And these rows with pivots in the reduced matrix, these will form a basis for the row space of A. Okay. So in this example, we had these first 3 rows in the reduced matrix that had the pivots in them. So all I'm going to do is take these 3 rows, and if I write them as vectors, then these 3 vectors will give us this for the row space. So this was the first row of the reduced matrix. This was the second row of the reduced matrix. And then this was the third row of the reduced matrix, okay? So you can confirm that. Okay. And then something that's worth noting is that the rank of A, so as I noted earlier, it's the dimension of the column space. But you'll also notice that it's also going to be the dimension of the row space as well, because you can also get a basis from the row space by taking the row pivot. So you'd be getting one big vector for each pivot. So hence the dimension for both spaces will be the same. They'd both be equal to the number of pivots. Okay. Yeah, so just take the rows in the reduced matrix that have the pivots in them. That will give you a basis for the row space. The next easiest one to get would be a basis for the null space. So to get a basis for the null space, so remember the null space was the solutions to AX equals 0. So you will need to actually work out what those solutions are in order to find the null space. So from the reduced matrix, I'm going to write out the corresponding system of equations for the null space. Okay, so from the first row of the reduced matrix, I get 1x1 minus x3 plus 1x5. You set it equal to 0 for the null space. The next equation would be 1x2 minus x3 plus 2x5. And then the third equation is going to be just 1x4 minus x5 equals 0. And if you remember the usual procedure for finding the null space at this point, finding the solutions. So since the third and the fifth columns are missing pivots, I'm going to choose x3 and x5 to be my free variables. And what I usually do is I assign a parameter to each free variable. I use s and t for my parameters. And then I want to solve for the remaining variables in terms of these parameters. So for instance, x4 will be equal to x5, so it'll be equal to t. x2 will equal x3, which is s, minus 2t, whereas x1 will be s minus t. And then what I'm going to do is I'm going to write this out in like a vector format. So putting the x's into a vector. I'm going to take the right-hand side and write it as a linear combination using the variables, the parameters as the coefficients. So this is what we were doing in the first couple of examples, where I was trying to find a basis for various spaces. So the strategy was to take a generic element of your space and then write it as a linear combination using the variables as the coefficients. I'm doing the same thing here. And so the idea is these vectors that we end up with would give me a basis for the null space, just like how I did in all the other examples that we did at the beginning. If you remember, these were called the special solutions. So here you can also kind of see why they're kind of special, because they give you a basis for the null space. Okay, so any questions about that? So then lastly, I guess I'll quickly touch on the last space, which was the left null space. Okay, now to get a basis for the left null space, this is the one that always requires a little bit more work than the others. Yeah, pretty much is, it's pretty much the same, yes. All right, and I'm just gonna end with this then. There's more that I wanted to talk about, but I'll have to save it for next time, I suppose. Okay, but to get a basis for the left null space, we're gonna need to do a little bit of work for that. Here's what I recommend. So the general procedure would be to take the basis for the column space that was previously found, put the vectors into a new matrix as the rows, and then find the null space of this new matrix. And the null space of this new matrix will actually give us the left null space. And then from there, we will be able to find a basis for the left null space. Okay, so this was the basis for the column space that we found earlier. It was simply the first, second, and fourth columns of our original matrix. So we would put these into a new matrix, but as rows. Okay. And then we need to find the null space of this matrix to get the left null space. We won't finish this example, but you'll put into REF to find the null space, just as we did for A. And you get a basis, and the basis that you get here would end up giving you a basis for the left null space of A. You can kind of see how it works. So remember, the left null space is just a null space of A transpose. So by writing these columns as rows, that's kind of reflecting transposing our matrix. And then we're just finding the null space here to get the left null space, okay? There's more that I can talk about, but I'll have to save it for next time.